Okay, thank you very much, Christoph, and thank you everyone for coming. I'm so delighted to be here. This is my first Design Modeling Symposium, and so far I've just been thrilled by the work that I've seen, and I'm excited to see what else is presented today and in the next few days. My talk today is going to be about a subject that I'm very passionate about, and I think fits the theme of this conference, which is how to bring creativity into performance-driven design. And like ACHIM, I'm going to have some videos to entertain you. This one's a much older one than some of ACHIM's. So this is all of our ancestor. This is a person named Ivan Sutherland, who, as a PhD student at MIT in 1963, invented a software system that is the foundation of nearly everything we do today in computational design. This is the first CAD tool. Ivan invented object-oriented programming in his PhD dissertation. Graphical user interface, computational geometry, even parametric design was all invented in this amazing tool called Sketchpad that is available for viewing on YouTube if you guys are ever bored. I highly recommend. There's about 20 minutes of this that you can watch on YouTube. And to me, one of the most exciting things about this very early tool for design is that it still feels futuristic. It still actually has functionality that we haven't achieved today in the ways that it combines performance and flexibility and the opportunity to be creative while also being precise. And so I think we all have a lot to learn from Ivan, and our history since him has been kind of an interesting mix of a focus on performance and a focus on the role of the designer in the computer age. So as Sophie so beautifully told us earlier today, one of the other really important events in the history of our field was the design and construction of the Sydney Opera House, and especially the work done by Ove Arup and partners, who were the first to really use finite element analysis to enable and empower the design of a very complex system. And in 1963, a lot of the engineers who were working in computational design at Arup got together for a symposium, the Symposium on the Use of Computers. And part of it was about exchanging knowledge, like what we're doing today, about technical tricks. But there was also a lot of worry. At this time in 1963, people were very concerned that computers were going to replace them as engineers and designers. And one person said at this conference as a way of reassurance is that the computer really can't take away the act of designing from the architect. The essential thing to remember is that the computer doesn't possess an imagination. And I'm not sure if this person really believed this or if it was sort of a consolation of what was to come, but this theme is, I think, permeated and kind of raised questions about our use of computation up until today. In the 1970s, Charles and Ray Eames were grappling with similar questions. In an exhibition here in Paris, there was a list of provocative questions, and one of them was, ought form to derive from the analysis of function? And their answer is, the great risk here is that the analysis may be incomplete. And I think this again applies to us today, that we like the idea of using calculation in our design processes, and yet we loathe the idea that we might completely encapsulate all of design into a computational process. The field of structural optimization, and originally called structural synthesis, is another important instance in this era. Starting in the 1960s, aerospace engineers with grants from NASA developed the fundamentals of what we now know as structural optimization. And through the 90s, this was a field that matured and developed primarily for engineering. And as we've learned more about it in the architecture field, I think we also have mixed emotions about it. On the one hand, when it produces forms like this that I consider beautiful, I think we consider it to be a really great tool that can help us as designers. But on the other hand, sometimes optimization can be kind of a dirty word. Not necessarily here among us. It seems like optimization has come up a few times in a positive way this morning, but in general among architects, often I find that people are very opposed to the idea of optimization because why would we let the computer tell us the answer to a design problem? We're the authors, we have agency, and we're the humans. And so what is the role between the computer that's calculating and the human that's designing? Even this conference, I think, talks about similar themes. This is the brief for the conference. where it's asked, are humans really being controlled by the algorithm? Again, this is basically going all the way back to 1963, where the Arab engineers had the same question. And it shows that we're really unsure how we feel about this. We want to use performance in design, but we don't want to be totally controlled by it. We don't want to have no flexibility, no authorship, no agency. We want to be creative, and we want to be designers. And yet, we can't be completely free as designers today. I think those of us who recognize the world we live in know that we're in a world of limited resources where global climate change is causing more and more issues for everyone, and the amount of energy and materials that we use in buildings play a significant role in this. This is from a colleague of mine, Catherine DeWolf, whose research shows that the Beijing Olympic Stadium uses 14 times the embodied carbon per seat as the London Olympic Stadium. 14 times, that's pretty significant. And does that mean that all buildings should be the London Olympic Stadium? Probably not. But it does mean that I think performance should play some kind of role in design. Personally, I'm not that worried about this idea. I think many of my favorite buildings and structures that from around the world, and some of which we've seen again today, illustrate that this does not necessarily have to be a deterministic process where optimization or the integration of engineering leads us only to one answer. These are all projects that have structural thinking embedded into their design, and yet they differ from each other very significantly. They're different in terms of their geometries, in terms of their structural action, in terms of the materials they employ, their means of fabrication. And so to me, this shows that the ideas of engineering and integrating that early in the design process can actually be an empowering and enabling tool for creativity rather than one that confines and constrains us. And today, one question that I think a lot of us are interested in is how do we take advantage of this kind of creativity in structural design with computation? And so that's the mission of the group that I lead at MIT, Digital Structures. And this is some of the people from the team. And so we're a diverse group of architects and engineers who are trying to figure out how to use computation to enable and empower creativity early in the design process with the integration of performance. And one of the first ways we do this is with the design space and thinking about how to explore it. In conventional tools that are used widely in practice today, there's a big disconnect between the tools for design and the tools for analysis. The tools for design, as we all know here, are incredibly powerful. This is a very outdated image from 2013, and so today we have even more powerful tools, and the ability not only to represent form but to generate it is something that's transforming the way we think of design. And yet many of these tools, as they currently exist, are mostly about geometry and do not necessarily integrate a sense of structural performance or evaluation. And on the other hand, the tools that are conventionally used by engineers are also very powerful. Since the 70s, finite element analysis has progressed to include many different types of loading cases, many different types of structural behaviors, and yet you need to know every single thing about your design before you can use these tools. You need to know all of the geometry, all of the materials, all of the boundary conditions. It usually takes quite a long time to input all of that into your software tool before you can even run this. And so there's not a good opportunity with conventional tools in practice to have any kind of interaction between these two functions that we're interested in. And so that's where this idea of the design space comes in. This is basically a parametric design space that many of us are familiar with. In this case, this design space is very simple so that we can visualize it. We're trying to find a shape for this truss, which is supported on two sides, simply supported with a point load in the center. And the idea is that as we change the shape of the truss, the amount of material it needs also changes. If the truss becomes very shallow, the material we require becomes infinite. If the truss, if that lower left node flips up above the supports, we find another region of high performance. And using any kind of structural optimization tool that was developed, let's say in 1970, we could find both of these solutions to this problem. One is a truss that's very similar to the one that we started with. That's the local optimum in this problem. And another is this truss all the way up at the top, which is the global optimum, which uses the least weight in this entire system. This is great, and like I said, we've been able to do this since the 70s, so why don't we use this more in contemporary design, especially at sort of the global scale of form making? I think part of the reason is because it's impossible to actually formulate the problem that we're trying to solve in the design of buildings. Structural weight is one metric of how well a structure performs or a building performs, but it's by no means the only one or even one of the most important ones. There are so many qualitative goals in the design process that we're always considering: the perception of space, the experience of humans, the appropriateness in the context, cultural, social, poetic aspects of design that can't be mathematically written down and solved with a 1970s optimization algorithm. And so I think that means in many times we just throw these away and say, these are very cute for little problems like this truss, but in reality we can't use these in design, and so we might as well not use performance at all. But I think there are some other alternatives. If we just relax a little bit and move away from an obsession with a single optimal solution, we start to see more possibilities. And so in this case, these three columns of trusses show designs that are 10%, 20%, or 30% worse than the absolute best design in the space. And what we see as we move away from the optimal solution is that, first of all, our performance is probably still reasonable. It's okay if we're 20% away from the best possible solution in the whole design space, and also that more visual and formal diversity becomes possible. And so maybe one of these designs that's not the absolute best in terms of structural weight is the holistic best in terms of meeting all of our goals, in terms of combining our need for structural performance with our need to fit a duct through the building, with our need to evoke a certain experience of space, with our need to connect to the architecture of our surroundings. And some of those things we can quantify and mathematically give to the computer, and some of them we can't. And so I think we need tools that allow us to play on both sides of that equation. The first tool that I made that tries to do this is a simple tool that works on online in a web browser called StructureFit. And it works on these two-dimensional trusses. I'm sorry if you don't like trusses. I like them a lot, so I'll have a few examples with them. So these 2D trusses are presented to us by the computer. And what it's doing, it's using something called an interactive evolutionary algorithm, which works a lot like a genetic algorithm, except the human helps play a role in determining which designs should be parents in the next generation. So here the computer is showing us 10 out of 75 designs that it randomly generated. And underneath each design is a number, which indicates the amount of material required. So it's running a little finite element analysis in the background and giving us a material score. Something less than 1 means we're using less material than this boring initial design on the upper left corner that's just geometrically regular. And so the user is able to interact with the tool by selecting the designs that are most interesting for whatever reasons he or she wants, whatever qualitative or quantitative reasons. And the computer uses those as the parents of the subsequent generations. And so there's a co-evolution process, basically, where you're navigating across that design space, not necessarily directly towards the optimal solution, but the computer is nudging you in that direction because it's always showing you the most elite designs out of all of the ones that it's generated. So together, you and the computer are deciding how to explore this design space and hopefully finding something that represents a compromise or a balance of quantitative and qualitative goals. In this particular tool, there's another step where you're also able to make changes in real time. I think real-time feedback is a very important part of performance-driven design. And so here we can see, as we try different options, we can see the forces in the members and we can see how the score changes. And although this is a very simple tool and uses really a very simple structural system, many structural types can be, or many structural shapes can be represented by trusses. We can think of a truss as an abstraction of force flow through any kind of solid. And so we can use this tool to help us find interesting shapes for buildings or for structural systems. And so here's an example of lots of different structures we can discover with this tool. On the left are the initial ideas that are all geometrically regular. And as we move from left to right, the performance score is improving. And all the way on the right are some some of our old friends, one of which is here in Paris. So we see that some of these designs that we've seen before come out of the tool, which is a kind of non-rigorous validation that it's able to find high-performing designs that have been discovered through other methods in the past. But it can also find designs that don't necessarily represent some kind of pure analytical solution of the absolute best in terms of something that we know how to describe with numbers. Maybe some of these other designs are best at this sort of hard to describe balance of goals that we can't necessarily write down, but that we know it when we see it. And so this can become a brainstorming tool that's not only calculating what we tell it to calculate, but helping us to understand our own goals and our own preferences as designers by suggesting things to us and having us respond. We've extended this tool to a more general approach that works in Rhino and Grasshopper. So as an example, this is a roof that we used as a motivation for this, a three-dimensional space truss that we can now describe very nicely using modern computational geometry tools with relatively small number of parameters. And so we have a tool in Grasshopper called Storm Cloud, which is basically the same thing as structure fit, except it's completely flexible, works with any type of geometry, any type of numerical evaluation, so it could be based on a finite element analysis, or a daylighting analysis, or a building energy model, or something else that you can describe yourself. And it creates different options for designers to consider, and evolutionarily combines them to help you explore the space in a way that follows your preferences. And so here it's trying lots of different options. You can think of this kind of like Galapagos or GOAT if you're familiar with it, but instead of always just giving you one answer, it's helping you create a catalog of ideas, it's helping you brainstorm, and it's always giving you information about performance, but also trying to create diverse options. And so with this tool, we can, again, explore this relationship between structure and shape. So this is this initial design for this roof, which is geometrically regular. And by changing the shape of the roof, we're able to save material, sometimes to pretty significant degrees. And there's not one solution that saves material. There's an optimal solution, but there are many options in between the initial guess and the optimum that are interesting and maybe solve the problem, the holistic problem, best of all for us. And so this is the kind of catalog that I'm interested in producing with tools. Instead of finding a single solution, it's I think, instructive to produce these catalogs that give us ideas and help us brainstorm and give us options. And in this way, the computer can move from purely calculating what we tell it to calculate to starting to suggest and helping us brainstorm. There are many types of catalogs that we can present. This is a different example where we're trying to find places for shear wall lateral systems in tall buildings, so finding the locations of reinforced concrete walls. We can apply a very similar approach to combine architectural goals and structural goals to find creative solutions. And we can also apply similar ideas when we have more than one quantitative objective. In multi-objective optimization, we have priorities that trade off with each other, where you can't improve in one goal without worsening in another. And this group of designs is called the Pareto front. And we have very good algorithms these days that can find those designs for us and, again, produce a catalog of options that represent possible solutions for designers that might spark ideas or help us brainstorm. And so we've applied this, for example, to studying trade-offs between the structural embodied energy in materials that we use at the initial construction of the building, as opposed to the energy that a building consumes during its lifespan. And in many cases, when formal changes are involved, there is a trade-off between those two objectives, even though they're typically considered only in isolation. Another interesting trade-off that we've seen a little bit today is to include the idea of constructability into the design process. And again, there's often a trade-off between something that performs better structurally but is harder to build, or something that's easier to build and performs worse structurally. And again, we can use these tools of multi-objective optimization to create catalogs and understand how they perform. This idea of catalogs is not necessarily new. Heinz Eisler famously proposed this catalog in 1959 of possible designs for shell structures. This is one of my favorite images. We've added these little bars. So basically, with computational design, we can start to get at the brainstorming and diversity of options that Eastler was thinking about, but we can also start to add quantitative information. And so we have a suite of tools in my group that we've been working on over the last few years that do a lot of these functions for us. I showed you Storm Cloud. We have a tool called Mu that finds Pareto fronts in Grasshopper. And then we also have a lot of smaller components that help with varying versions of these workflows to generate different types of catalogs. This is on our website, and we also just released it open source. So if anyone's interested in playing with these tools, I'm happy to give you the information. Okay, so the design space catalog is useful, I think, but it's not enough in itself. The design space catalog is also, has precedent in a lot of other research before me. This is an example from Richard Balling, who in 1999 wrote a paper called Design by Shopping, A New Paradigm. And this is my image. This is not from Balling, because I decided to put some images of women on the screen. But this is a shopping catalog where we have different options of designs that we might be interested in. And one important thing is that underneath each design, there's a number which refers to cost. If we think about this shopping metaphor just a little bit further, one place that you might go shopping is Amazon. I don't know if that's popular here in France, but in the US we use Amazon quite a lot. So for example, Peter Rice's famous book, An Engineer Imagines, is newly back in print. Highly recommend everyone buy it. Whoever made that happen, thank you very much. But Amazon allows us to buy this, but Amazon also has some other functionality. So it says customers who bought this also bought these books. How does Amazon know how to do this? Many kinds of websites have a similar problem. Netflix, a famous movie streaming service, similarly has this very famous algorithm for suggesting movies to you that you might like based on what you've already seen. A few years ago, they had a prize for $1 million for someone who could write a new algorithm that was better than the one that they were currently using. So this is an important problem, and it's the similar problem that we have in design space exploration. Without these kinds of algorithms, we have this rabbit hole problem, having so much content that users get lost. And this happens in generating design space catalogs as well. Just because we can generate millions of possibilities doesn't mean we're going to find the right ones, especially if we have a lot of design variables. And so we need to have more intelligent systems to simplify and control our design spaces. This is another motivation for why this is important. This is going back to the 1980s, when people were first starting to use computers in the office. And there was a theory, and this is experimental research, about if the computer is too slow, you lose your creative flow. And your ability to complete creative tasks diminishes the slower your computer is in responding. Delays, these are the result of poor tools or the poor deployment of tools. And this is a problem in design as well. I think all of us have had a case where we're trying to use a tool and it's taking minutes or hours and we forget what we were working on, or we lose the creative flow during that delay. This is especially hard when we're trying to use simulation and performance evaluation early in the design process, because often those simulations can be time-consuming. A building energy model is not necessarily instantaneous. A complex finite element analysis is going to take at least a few minutes. And so on. A lot of these processes, even with modern computers, are still slow. And so to solve that, one of the things that we're very interested in my group is something called surrogate modeling, which is a way to approximate a design space, to approximate performance using machine learning so that you get instant feedback on your designs instead of waiting for the full slow analysis. And it's a very simple process. It works it's basically just regression, which I'm sure many of you are familiar with, where we have some slow process on our computer, and we can simulate a few data points using that slow process. And then we can create a model based on those data points that is instantaneously to query, so that all new data that we're interested in, we can get an instantaneous prediction of performance. This is very powerful because it means that our tools that might have originally been slow can now be very responsive and very interactive, and can enhance creativity, I think, by allowing us to remain in this creative flow while we're working. So on the right, we see we have this speed up available to us, and on the left, we don't. And I think you'll agree that it's always preferable for our computers to be faster. And And with this surrogate modeling technique, it's possible not only to make things faster by making your model simpler, but also it allows us to bring in more complex performance analytics that we would never have been able to bring in before. So this is another example where, in this case, we're interested in evaluating the photovoltaic potential, basically the ability to generate energy with a roof, which involves doing an annual daylight analysis where we're simulating every hour of a year, which can be slow. So in this case, we've built this surrogate model with the blue dots, and then we use that model to predict performance of the black dots. And we can see it's not too bad, and it allows us to really quickly go through a lot of design iterations and understand how that performance can play a role in the generation of form. Another thing that's important in these design space catalogs that we're generating is that they're giving us designs that we're interested in. If we see lots of designs that look the same, it's not very helpful in a creative brainstorming type of process. And so we're also working on developing metrics to measure diversity in the design space that we're calibrating with real human perception through a lot of experiments. And with these tools, you can see in this bottom row, where it's a lot easier to produce designs that are visually different from each other. I think that's another really important feature in this process, because otherwise there's this boredom of seeing something that looks very similar over and over and over. And finally, there are other ways that we can start to use data science to understand design spaces. One area that I think is really exciting is something just using clustering, which is a very common technique in data science and other domains. But what it means is that we can start to identify families of designs that are similar to each other, so that instead of presenting a designer with 10 million possible solutions, we can say there are 10 general families of possible alternatives that you might be interested in. And if the designer likes a representative design from one of those families, they can start to drill down. And you can see here how the clustering works. Basically, it can start to group designs that have similar features in the design space and significantly really simplify the number of options that we have to look at. So this is also something we're working on from a tools perspective. So these tools are also available, or they will be available very soon if they're not already on our website. Now I want to move beyond the idea of the parametric design space more broadly to think about the idea of diversity, which I think is so critical for performance-driven design when we want to be creative. So these are some examples from sketches from some famous engineers. The one on the left is from Georg Schleich, and the one on the top is from Tony Hunt. And these are conceptual design sketches that were done by hand that, to me, represent the goal of what we might want our computers to be able to do if we really want them to help us brainstorm and suggest alternatives. One of the things we see is that the designs are not only different slightly in terms of their geometries, but a lot of them are typologically different from each other. They're not necessarily, one is a suspension bridge and one is a cable-stayed bridge, one is a truss. Can we generate all of this diversity, this range of options with a parametric model? Maybe, but I haven't been able to figure out how to make a parametric model that contains this breadth and this variety in a single definition. And so in that way, I think the tools that we're using in parametric design still really fall short. So are there other ways that we can formulate design spaces that are broader and contain more diversity and the potential to surprise and delight us? One possible way is moving again beyond the parametric design space and thinking instead about rule-based design, which is an idea that's been percolating at MIT since the late 70s and has produced varying interesting results. But one of the things it's really good at is producing diverse results. So these are three houses in the style of Frank Lloyd Wright that were produced with a grammar. And to me, what's interesting not only is that they look like Frank Lloyd Wright houses, but that they're very different from each other. It would be very hard to make a parametric model that could produce all three of those options. And so I'm interested in doing that, but maybe from a structural perspective, in writing a grammar that includes rules not only about geometry, so this is an example of a rule for generating bridges, but also rules that incorporate structural behavior and performance so that all of the designs that are generated are structurally possible. So this is an example of a grammar that I've written to generate possible bridges. And what's really exciting about this grammar for me is that all of the designs are generated from a single program. Basically, I press a random generate button 3 times, and I get these 3 different bridges. I think they're significantly different from each other. If I press it 50 times, I get this. So all of these are generated from the exact same program. I'm not doing anything to change them, and the design space is, I think, much broader than what's possible with a purely parametric design. We can see some sort of normal designs, but also a lot of designs that start to span typologies or indicate new suggestions to us to help us brainstorm and help us think about options we might not have considered by ourselves. An extension of this work starts to think about an even broader problem. What if we just have a blank page and we just know the location of a load and the location of supports? We can use something called graphic statics to help us generate structures that are always guaranteed to be in equilibrium, but also are otherwise completely open. We're basically just materializing a system of forces with a lot of possible variation in how that happens. And so again, this can lead to really interesting structural solutions, not necessarily ones that are structurally optimal, but ones that are guaranteed to be in equilibrium, and that might show us ideas that we haven't thought about before and that we might not have discovered on our own. Another important topic, I think, in this world of creativity and design is this idea of intent. That's a huge part of the architectural design process. I'm very inspired by this project that Sophie showed us earlier today, the Pavilion of the Future by Peter Rice. And in this case, the design intent is a geometric one that's fairly simple, but I think incredibly elegant, where these masonry blocks are forming a semicircular arch, which we know is not a funicular shape. It's not the right shape for an arch that wants to be in pure compression. And so the way Peter Rice makes this work is by applying this tensile post-tensioning structure in steel to put radial forces into the arch that are large enough that the dominant loading becomes radial, and the circular arch becomes the right shape for the loading that he's applied. So instead of taking loading and figuring out the form that we need to meet the loading, we can change the loading to meet the form that we're interested in. So a few years ago, some of my researchers and I came up with a way to formalize this, again using graphic statics, where we can basically start to draw the equilibrium of the structure, find where the equilibrium is not complete, basically find where the force polygon doesn't close, and then add those forces back into the system so that we can make the structure work in pure compression and pure tension. And what's really nice about this is that it works for many different shapes. It's not only parabolas or catenaries or semicircles, but any 2D curve can be made to work in pure tension and pure compression through this application of additional forces, and we can use graphic statics to help us find that. Now that doesn't mean that all of these structures are very efficient. Some of them might still have very high forces in them and be susceptible to buckling, but this technique at least allows you to start to understand the tensions between the architectural geometric intent and the structural possibilities without forcing us to snap to one side or the other. And we did a little bit of validation of this. We've built some physical models. So here we're cutting the post-tensioning curve just to prove to you that it was in equilibrium, and now it's not without the addition of the tensile forces. And more recently, we've been trying to figure out how to do this in 3D, where we'll have a 3D structure, again, that's not in pure tension and pure compression, that's basically not in equilibrium without the addition of bending forces. And using some recent developments in 3D graphic statics, we're able to, again, make this work in pure tension and pure compression by finding the forces needed to put this in equilibrium. And again, we found that this works with physical models. And I think this is exciting because it means that our geometric palette and our desire to be structurally efficient don't necessarily have to be pulling us in 2 different directions. We can use these types of ideas to meet both goals at once. I explored a similar idea recently in a studio I taught with the artist Janet Eckelman. I don't know if you are familiar with her work, but she does very large-scale tensile structures on the scale of cities with these amazing nets. And we talk about her work with two nets. There's a hard net and a soft net. The hard net is basically the tensile net that's stretched up above, that's suspending the weight of the structure. And the soft net are these incredibly flexible fishing nets that move and play in the wind. And so we were working together on a design studio at MIT to come up with an installation for Philip Johnson's glass house. And so we called this the soft house, and the students designed this idea for a meditation chamber to be suspended in the trees outside of the glass house, which you see here in the distance. And because of Philip Johnson's interest in pure geometries, the students decided they wanted this glass house to approximate a sphere as best it could. Sorry, the soft house to approximate a sphere as best it could, which is an interesting contrast between the sort of hardness and rectilinearity of this house and the softness and curves of this meditation chamber. And so again, we use tools of design space exploration and sampling and optimization to try to figure out this goal. And in this case, our goal wasn't necessarily to be as structurally efficient as possible, but it was to be as close to a sphere as possible. And so these same ideas of exploration and sampling and developing catalogs of alternatives can be used to help us meet our design goals, even in systems that are constrained, that have to be in pure tension, like this one. So here we did a lot of photogrammetry to develop these 3D models of our site. We actually built a version of this on the campus of MIT. These are just some more renderings of it. And we built this with students in a very short period of time, so we did not exactly achieve the perfect sphere. But I think it was still a really interesting project, and we got to test out a lot of these ideas. Okay, so finally, most of my talk is about design and creativity, but I just wanted to talk a little bit about materialization, since that's such an important theme in general today. And like many of you, I'm interested in how these processes which generate interesting forms, in this case, potentially structurally optimized forms for lattices, can be materialized. And digital fabrication offers unprecedented opportunities for this, because complexity, if maybe not free, is a lot easier when we can use robots and digital forms of making. And so in this case, we're working with a similar process that we've seen from some other people today. We're working on 3D printed lattice structures with an extruder mounted on a 6-axis robotic arm. And we're interested in these really as possible structural systems for buildings that could be optimized and shaped according to the forces inside them. So in this case, we just built a regular rectangle, and we have this very fancy lab at MIT for structural load testing. So it'll commence, here it goes. So there we go. We also have another lab, but this is our quick first test to study how these behave. And we were able to, through trial and error, design joints that ended up behaving much better than our initial option by being careful about how we were doing the extrusion. And then we could apply this technique to a beam that had a shape that was driven by structural performance and our creative goals, which I think is potentially both beautiful as an object, but also this beam is about 30% stiffer than one that is a regular extruded rectangle. And so the possibility of making every joint different, which the robot doesn't care about, is really appealing for starting to explore this structurally driven design. And we've been working on this in collaboration with a company in the United States called Branch Technologies, who has a much bigger robot and a much better material. This is a carbonized ABS material that they're using. They print a very large cruciform cross-section that's pretty good at resisting buckling. And so we're starting to look at these as potential building scale components that maybe today are a bench, but tomorrow could become a beam that's supporting the roof of this building. So I think I'm doing okay. So before I conclude, I want to do a quick advertisement, a little cross-fertilization. So if any of you guys, I think a lot of you guys, all the talks I saw today were really exciting, and they were about the intersection of design and creativity and some amount of technology. And if these topics are interesting to you and you want to come to MIT, we're having this really exciting conference next summer, the IASS Symposium. This will be the first time in 24 years that it's been in the United States. So I hope to see many of you there. The abstracts will be due, I think, in January. And so to conclude, I think there are many different systems and tools and possibilities that are available to us today that we can explore. But in all of them, I hope you will agree with me that performance can play a role in creative design if we're using these digital tools in a creative way. Thank you.